So we are hopefully going to get to the value iteration and policy iteration for the Infinite Horizon case of Markov decision processes today. One thing before I forget, I'll just write this for the people who might come later. There's a small possibility that I won't be here on Wednesday, but I will know about that only tomorrow. So I'll let you know beforehand. So either way, you will hear from me. If you don't hear from me, come to the class. Okay, that's the persistence assumption. Okay. That's an epsilon possibility, 0 less than. Okay, so that's just, I'm just telling this, and once I know tomorrow, I will send you an email if in fact I'm going to miss the class. Okay, and then as to what I'm going to do to make up for it. Okay, so other questions before I start?
Something about assignment.
What happened? What is the question?
The first thing is like we need to type it and print it and give it to your written notebook.
Handwritten would be fine. I mean, as long as the TA can read it. Okay. But program, you actually need to write the program. It's not going to be easy.
Can we turn in its punch cards by any chance?
Yes, unless you want to get punched here. By the TA. Me, I'm a non-violent guy. But anyway. So, any other questions on that? I mean, there are some of the things. There was actually a question about policy iteration on the blog, on the forum, and we didn't even cover it. So, in fact, it's I'm not going to get that. Though some of those probably, hopefully, will make more sense at the end of today's class. Okay. Any other questions? Okay. So we were doing the simple finite horizon Markov decision processes. That means you know exactly how many epochs. I mean, they use the word epoch. Decision epoch. So in a finite horizon Markov decision processes, you only get to make T separate decisions. That's it, T being the horizon. Okay. At the end of that, essentially, you don't get to act anymore. You're done. Okay. And that was the case we were looking at. Then we will see today, of course, from there we'll go to infinite horizon. Infinite horizon means essentially the behavior can be infinitely long. Okay. Now it turns out that actually it's nice. It turns out that it's actually not that hard to extend the theory to infinite horizon, and in some sense becomes simpler when you deal with infinite horizon cases. But what's more realistic is, for example, how many decisions do you have to make before you disappear? It's kind of finite, but it's not a definite horizon. Do you see what I'm saying? It's not infinite. None of you are going to make infinite number of decisions, but neither is it exactly 10,000 decisions and that's it. Okay, so that is the more interesting case, and that's called the indefinite horizon. And we will actually do this first, then this, and then that a little. Okay. The models actually, MDPs are used by different communities for very different uses. Okay, we are looking at it from the point of view of an agent actually, behaving in an environment. Originally, they came up in operations research community for making sequential decisions, where the number of stages has a natural connection to the problem. Okay, so in fact, OR looked at decision epoch, the finite horizon MDP is much more. Okay, if you are thinking in terms of planning, in terms of what is my best action to do, not knowing exactly how long I will live, then really what you need is this. So planning people are sort of more interested in the indefinite horizon MDP problem. Okay, nobody is really interested in infinite horizon problem, but in fact, reinforcement learning people use the infinite horizon MDP as their base model. Okay, when we get to RL, you'll see that that's what they'll use much more. Okay, so those are the sort of, three models for fully observable mark codation processes that we'll care about. There are many more, and in fact, even if it is fully observable, there are many more special cases. And then I told you last time, there are a lot more as you start throwing in partial observability, multiple agents, durative actions, etc. Yes?
Will we be covering the indefinite horizon case?
We will, a little.
Okay.
Okay? Yes. Okay, so in fact, we will, that's why I'm going to use that term, that's why I'm sort of mentioned it before today. Okay? I'll be using it today. The simplest case, conceptually, is the finite horizon case. Okay? And the interesting thing, of course, is for the finite horizon case, the policy is more complicated looking because it is indexed off of the number, the time to live, time to go. Okay, so if you have 100 years to live, then do this. If you have 99 years to live, in this state, you should be doing this and so on. That's what we look at. So the policy looks more complex, but it's very easy to compute it, and you don't have to ask yourself, why does the algorithm converge? Because there are actually a finite number of stages, and as we mentioned last time, the V0, the V0 for the optimal policy, and if you know the V0 for the optimal policy, then you can always find, if you know Vk, you can find Vk plus 1. Okay, and then if you do these case stages, then you get the entire value function. Okay? And this is the one that takes a lot more precedence in the OR literature, especially the introductory OR literature, and textbooks and so on. Okay, so we looked at this as the last thing we looked at last time. So the idea is that when you are in the state and you have no more actions to do, then essentially all you can get is the immediate reward of the state. That's it. So V0 is the same as R of S. Okay, and then if you once you got V0, then you can compute V1 in terms of V0. And then you can compute V2 in terms of V1, V3 in terms of V2, and so on. Okay, so that's basically the value of the finite horizon one, and we look at that. So the way, couple of things you want to keep in mind is, where did the dynamic programming get used? The dynamic programming, in some sense, is being used because you can do Vk in terms of Vk minus 1. Okay. And that depends on the fact that how you reach a state doesn't decide what reward you get in that state. The reward of a state only depends on the fact that you reach that state. And the value of a state only depends on how long you have to live now that you are in this state, not how you got here. Okay? Because of that, you are able to do the dynamic programming. And so you can compute Vk with V1 in terms of V0 and so on. Okay. And then because of the finite horizon, the policy itself is non-stationary, even though everything else is stationary. Right? The reward is stationary, the dynamics are stationary. Do people see that dynamics are stationary? I'm really worried now when people are looking. The dynamics are T, S, A, S dash. Okay? Those probabilities don't depend on how long you have to live. Once you do the action A in S, your probability of getting to S dash is the same whether you have 2 years to live or 1 year to live or 15 years to live. Now, if you only have 0 years to live, you won't ask this question because you won't be doing any action. You see what I'm saying? So dynamics are stationary, reward is stationary, but value is not stationary because value depends on how long you have to live. Okay, value is not stationary, and so policy is also not stationary. Okay, and then the complexity for the finite horizon MDP, essentially what we did is basically this is value iteration. What we actually think of this, what we did here as value iteration, because we will talk about value iteration more for infinite horizon things, but in essence, it's actually iteratively you're computing the value of V1 given V0, V2 given V1, and so on. And the number of iterations are fixed in this case. Okay. So the complexity of this is that in each iteration, each of the n states computes the expectation for the number of actions you can do from that state. And there are A actions, right? And then each expectation takes n time, O(n) time, okay? Because, and then so basically the total time taken is dA n square. N square is n is the number of states, you are quadratic in the number of states. The t comes in because you do it once for each stage. The iterations are t. Okay, so this is a simple complexity of this problem because you know exactly how many iterations are going to happen. Okay, and it is considered pretty good if you think the input is in terms of states. Because if the input is in terms of states, then if there are n states, you're only doing work that's quadratic in the number of states, some such a polynomial algorithm. If on the other hand, the input is given in a compact representation where states are represented in terms of state variables, then basically the input is logarithmic in the number of states, and so this is suddenly exponential in the input. Okay, and it depends. If you are setting up problems where essentially the number of states is carefully controlled, which is basically what happens when finite horizon MDPs are used in OR literature, then this is a pretty reasonable complexity to deal with. If on the other hand, you think your problem sizes are more, the sizes are more thought of in terms of the number of literals making up the state, then this is actually exponential in that input form. Yes?
So the n squared here is talking about the fact that you're checking each state and each possible destination state, basically.
Because the action, exactly, because an action can potentially, in the worst case, take you to every other state. Okay? If you happen to know some fixed width of the actions, that means each action can, from a given state, an action cannot take you to more than k states, then that will let it use. Okay? Anyway, so that's the complexity, and that's like polynomial, from number of states and exponential in number of state variables. Okay. So that's your finite horizon case. Okay. Now we want to deal with infinite horizon case where you don't have any limit on the number of epochs. You have infinite number of epochs. Okay. Now remember that the policy is indexed off of the number of iterations you still have to go, the number of epochs you have to go. Okay, time to live, okay, time to go. Okay. Now if you have infinite number of decisions to make in the beginning, and then you make one decision, how many decisions you have left to go? Infinite. And then one more, you still have infinite left to go. Okay, so just from that point of view, you can reason out that if there is a policy, if there is a optimal policy, it cannot possibly be non-stationary. Right? Because in essence, what are you going to index off of? You're indexing off of time to live. Time to live is infinite all the time. Okay, so that's a conceptually reasonable way of understanding that if there is an optimal policy, it has to be stationary. Okay, and so what that means is we don't think directly in terms of, so once the policy is optimal, the policy is stationary, then so is the value function stationary. Okay, so how good it is to be in this state does not depend on when you got to this state. It never depended on how you got to this state. It previously depended on when you got to this state. Because if you only have 100 years to left, and so for example, if you just completed your PhD, how good is it to be completing PhD? Well, if you are like 25, pretty darn good. If you are 99 and a half, not so good. Not at least as good as 25. Okay? Do you see what I'm saying? So, when you completed PhD mattered previously. Whereas if you're going to live for infinite number of years, it doesn't matter when you complete your PhD. Right? Okay? So, then essentially, that's the intuition you want to have, that basically you have a unique value function. If there is an optimal policy, it would be stationary, and then the value function corresponding to that would also be stationary. Okay, now, how do I compute that value? Basically, we talked about the fact that, if I give you a behavior, which is the sequence of states that you have encountered starting from a given state, then the value of that behavior is addition of all the rewards you collected going through these states. Right? That's what we did all along. That was the bedrock principle for us. The problem with the infinities is if you have an infinitely large sequence of states, then basically you're going to get, unless you're careful, essentially the summation will always be infinity. However small the reward is, if you just add up those rewards, then the summation can be infinity. If everybody is infinity, then there is no difference between any state and any other state. Okay? So, that is the first, in some sense, mathematical problem you have here. Okay? To even talk about policies, you need to talk about what is the value of an infinitely long behavior. Okay, what's the accumulated reward of an infinitely long behavior? An infinitely long behavior can have infinite value. And if it has infinite value, you kind of get. Yes?
But you can compare those two by how fast they reach a certain point.
That's that's an interesting, so actually, so again, the trick with MDPs is there are like these many books on MDP literature, and you can ask me interesting questions which will get me out of the little chapter you have. Okay, the question that was there on the forum was straight like that. And the question you are suggesting is a very interesting point. Sometimes when you live infinitely long, then what you are trying to optimize is not necessarily the accumulated reward, but the average gain, per certain amount of time. Okay, and in fact, there are, so basically all the MDPs we are looking at here, they basically consider this ELAV. Which is basically, you're looking for a policy that maximizes the expected accumulated reward you will get. If that's why you're looking, that's what you'll get. At least those policies won't be well defined. And you are very much right that had I been defining policies in terms of the average gain, then they will be well defined. But unfortunately, average gain MDPs are even harder to deal with. Okay, there is literature on it. Okay, those of you, by the way, who are into MDPs, because we will probably spend, one more or so week on just MDPs and then go into reinforcement learning. But given it's a graduate level course, every topic you can spend lots and lots of time. It's particularly true for MDPs. The classic references for MDPs, for any random question you might have, is Futterman's MDP textbook, which is only 700 pages long and only talks about finite horizon, finite discrete state MDPs, and they do care about average gain situation. And the other one, of course, is Bertsekas. He writes books the way people write papers. Guy has like 17 books, and he has at least 2 books. One is optimization, dynamic DP and optimization, volumes 1 and 2. The other is neurodynamic programming. The neurodynamic programming is actually relevant also to the reinforcement learning part, which we'll be discussing. it depends on how far you want to go into that. Okay, so I'm sort of giving you one reasonable type of MDPs that we will actually, that do make sense and that we can understand their algorithms. Okay, so average gain is not what we are looking at expected accumulated reward, and the accumulated reward has to be somehow be made finite so that you can still have a well-defined optimal policy. Okay, one way you can do it is, you know from grade school that you can always make a sequence converge if you make it a geometric sequence with common ratio less than 1. That's one way we know how to make. I mean, there are lots and lots of infinite, infinite sequence, infinite summation, which converge, and one very specific case is the power series where the common ratio is less than 1. Okay, so I know that. So I can use that to essentially say, I'm going to, if I have, say, well, my problem is that my agent is started from S0, went to S1, S2, S3, S infinity. Okay. Now, of course, they're not infinite number of states. These are the states from our state space, that were looked at, that you encountered at the first time period, second time period, all the way up to infinite. And then it got an R1 here, an R2 here, an R3 here, etc. R infinity. Right? And then if you want to add them up, you have to add them up. That's that's likely to be infinite. What I would do is I would essentially throw in a, I'm going to use the beta because I used beta in that slide. A beta which is less than, strictly less than 0 less than beta less than 1. Okay, actually 0 less than equal to beta less than 1. And I would start with beta power 1 R1, beta power 0 R0, beta power 1 R1, beta square R2, beta cube R3, beta power 8 R3. Okay. If I do this, I know for sure this sequence has to be finite as long as beta is less than 1. Because remember, all these rewards have to be from your reward function. And the reward function has to be bounded. That was part of the definition. Your reward function had to be bounded. If it is bounded, that means there is a max reward. Right? So this then is less than or equal to beta power 0 R max plus beta power 1 R max, beta power k R max plus beta power infinity R max. Right? So now I can remove the R max and I have, a sequence in terms of 1 plus beta square, etc. If you remember the grade school math, that is 1 by 1 minus beta is the summation for a geometric progression, geometric sequence with beta as the common ratio. 1 by 1 minus beta would be the summation. Right? Okay? And so for example, 1 plus half plus etc. that would become 2. That's the famous paradox. Okay, so 1 by 1 minus beta times R max is the bound on this. So I just proved to you that once I pick a beta, then I got rid of my problem, which is how to make an infinite sequence sum to a finite number. So now I can jump back into my math and just talk about what is the optimal policy with respect to this. Now one question before that is, well, you did this just so that the math will work out. Does it have any reason, any rationale for doing this? Well, so we invent rationale then. Okay, and in fact it has a pretty powerful rationale that can be invented. The assumption is the future rewards are discounted with respect to the current rewards. So in particular, would you like to take $1 now or $20 10 years from now?
$1 now.
Okay, so would you like to take $1 now? When you actually win the lottery, you have to deal with this, right? People deal with this when they win the lottery. I mean, of course, I know one, and maybe you did with it, but you know, this Powerball, etc., will say $30 billion or maybe $30 trillion. Who cares, right? Humongous amount that you can win, but then when you actually win, they'll say either you can take a lump sum, where if you're actually trying to take $30 million as a lump sum today, it will be probably, you know, maybe $10 million or something, because they will upfront take all the taxes off and then you do. Or they will say, as long as you live, you will get, you know, $2 million per year. Now, it's a trick question. Are you going to live long to make this work out? Or would you rather take $10 million and run? Right? And whether or not, and you know, I think different people do different ways. I mean, you know, basically, certainly people who have no children or don't like their children, and they are about 95 and they win a $10 million lottery, are going to take even 1 million of it right now, rather than get 500,000 forever, because they're probably not likely to live too long. Okay, so in all these cases, essentially, people are discounting future reward with respect to the current state. Okay, and so if the beta is closer to 1, I mean, my example of this is, you know, if you want to make interesting, you know, real life comparisons, then if you consider high school dropouts, undergraduate students, and graduate students doing PhD, okay, who do you think approximately, you know, if you are trying to make betas for them, you know, who do you think has higher beta? Grad students, because they are really, you know, PhD is an indefinite horizon problem. You know, believe it or not, right? You know, and one day you'll get done. And then you think that, well, the entire world is going to just stay for me when I get done, so that what looks like a great job in Facebook will still be there when I get done with my PhD. Okay, so I'm assuming that reward, you know, K years from now is reasonably highly valued right now. You know, and then there are people who drop out of, you know, PhD program and do masters. They think, you know, who the heck cares? Who knows whether Facebook will even be around? Okay, and then there are people who drop out of high schools, you know, who probably are thinking, who knows whether we'll be alive tomorrow? So let's just take what we get right now. Okay, so one way of making sense of the beta, this is only a rationalization, is that you can say the higher the beta, the more you know, you are giving weight to the future rewards with respect to the current time. Okay, and you are likely to do that if you think the world is likely to sort of continue in the current dynamics. Okay, and so my way of thinking about it is, if you don't have PhD students in countries with civil wars, because it's not worth it. You know, you cannot actually understand, you cannot believe that the dynamics of the country would be the same a month from now, let alone years from now. Okay, so you can think of, you know, long back people used to say that, you know, if you want to understand how good a society is, look at the status of the women in them. Okay, and that tells you how civilized the society is. And my version of it is, if you want to see how stable a society is, see how many grad students are there in that society. Because, you know, grad students are essentially, you know, voting with their feet, that we believe that this stuff is going to be around, so while we go around doing our PhD. Anyway, so that's all just, you know, fun rationalization, but really the reason we do it is so that these, you know, sums will actually add up to a finite number. Yes?
So do we take that in the finite horizon case, beta to be 1?
In the finite horizon case, you did not talk about discounting at all, essentially. You remember that the beta is now an extra property which is just coming out of nowhere. It's not part of the reward function. Do you understand what I'm saying? It's not part of the reward function. It's not part of the world dynamics. It's an extra constant I just threw in. Okay? That arbitrary decision did not have to be made in the finite horizon case. There was no reason for it. Okay, in fact, one interesting point, of course, is suppose you really do want to believe that even in the finite horizon case, there is a discount, you can do that. You can essentially do that by having, you already have a non-stationary value, non-stationary policy. If you were to allow non-stationary reward function, this algorithm will still work. Okay, and you can define non-stationary reward function to be, if you know that the inherent goodness of a state is R of S, then its goodness in T stages to go, so inherent goodness of a state is R of S, then you could say that essentially you would discount it by the number, of states that you still have, number of states from the initial. So if you have, this is your horizon T, and if you already live to K, then you're going to put gamma power KRS. That's one second. So that's one way you will get a non-stationary reward, and it will still work in this case. Okay, but there was no reason to do it, at least mathematically. If you believe in it, then you really believe that there is a non-stationary reward function, and that would be the same for every agent. Whereas here we are saying each agent gets to decide what their beta is, which is kind of a strange thing. Which also allows us to make all these nice analogies, but you make that. Yes.
So we use this sequence of state just to represent the state where agent will go.
Yeah, the states that. So you're seeing this, agent. The agent is following some policy. So and it's in a particular state. Then it looks at the policy and says, what am I supposed to do next? It will tell you the action to do. Then that action then picks the state you will get into. The nature will pick the state. So you notice that the agent has now gotten to S1. So it will get R of S1. Except it really is worth only gamma power 1 R of S1. And then if it gets into S2, then it's R of S2 is the immediate reward. But since I'm trying to decide 2 steps away, then it's gamma power 2, gamma beta. I'm sorry, by the way, I'll keep probably saying gamma when I mean beta. But that's partly because a lot of the literature uses gamma as the discount factor. These slides use beta as the discount factor. It doesn't really matter. So if I say gamma, I mean beta. Okay.
It's for us to, from outside to see, this is the sequence.
Yeah, but even the agent knows, right? It's like when you get into the state, you will feel it because it's a fully observable MDP. And what's more interesting is actually, here's another interesting point, that the reward is going to be felt whether you know which state you are in or not. Okay, so even when you get into partially observable worlds, where you don't know which state you are in, but you will still feel the reward. Right? I don't know which stove. There is a stove at the end. There's a cooking range here, there's a cooking range here, there's a cooking range there. I don't have eyes, so I don't know which one I am at. I put my hand, I will get the reward. Right? The reward doesn't depend on whether you can see the reward or not. You'll feel it. Okay. That's another interesting point. Okay. So, but here actually it's fully observable anyway. So you do also know the state.
So in this case, there will be some state. Suppose Sk will be equal to S1.
Yeah.
So we have a stationary policy.
So, but by the time you come back to that state, k iterations from now, the reward you're getting is now k. So gamma power k times the reward. If you got it right in the beginning.
So we are not considering the reward stationary at that point, and it will be multiplied by the gamma power k.
Yeah. You can think of it as that way. So the gamma is essentially setting up a non-stationary reward function. That's a very reasonable way to think about it. Because that's what you need to do for finite horizon MDPs to make it work with the gamma. You will essentially have, t different reward functions, one for each iteration. Yes?
See, if we are taking non-stationary rewards into consideration, I think that, for example, if a particular agent has taken one step and the reward function has changed, no matter how, so now the policy need to be revised. Because
no. Okay. One other issue is you can only plan with respect to the model you have.
that
Okay. MDP is all, right now what we are doing is we've been given the model. We've been given the transition function, reward, everything, and we are trying to find the optimal policy. if I were to tell you, I'll keep changing my model, then of course there's no point in making an optimal anything. Plans make sense if the world, the map more or less remains the same. Okay?
One last question. For example, if we have made a vacuum cleaner which works itself, okay, so now if the optimal policy is that should roam around the whole room and clean everything, and now immediately while it's cleaning, a child comes and drops something there.
But that is basically, that changes the environment. MDPs are assuming the environment is static. Okay? Yes?
If the dynamics are stationary, then we cannot use a discounting factor breaker.
Why?
Because because we're assuming cumulative. I'm talking just about stationary.
Yeah.
But if the dynamics do not change, then I mean in infinite horizon.
Please understand that what I mean by dynamics not changing is if I'm in S and I do action A, with 0.7 probability I'll get to S1, 0.3 probability I'll get to S2. These probabilities remain the same. If I come to S multiple times and I do this action, sometimes I go to S1 and sometimes I go to S2. I hope you understand that distinction. The only thing that's not changing is the probabilities. That's what the dynamics being stationary means. Okay? Again, many of these things, I mean, we can do, you can actually, this thing is being recorded, you can listen to it again, and if you have lots of questions, type them onto the forum, and that would be probably, some we should have, there may be many more, and that would be a much more efficient way to answer that, because it may well be that some others don't have it and you have it, and you should ask other questions you have, even if the past time doesn't have it. Okay. So, so where are we now? Okay, so as I said, basically the Argmax, using the Argmax, you know that every behavior is going to, every infinitely long behavior is going to have a accumulated reward that's upper bounded by this. Okay, that's why we know it's. And then this motivation stuff is what I was talking about all this while, making it rational for what we do. But from an algorithmic point of view, this just makes sure that the infinite sequence converges. Okay, so now the optimal policy is going to be stationary for the reasons I mentioned. If there is one, it's going to be stationary, and it will maximize essentially the value that you can reach starting from that state if you were to follow the optimal policy from the rest of it. Okay, so the value of a state, this is something again, you have to understand that the value of a state depends on the policy that you're going to be using. The optimal value of the state is if you're doing optimal policy starting from that state. And it's obvious, like, lots of people say go to college, going to the college as a state is supposed to have a lot of value. That's because people assume that after having gone to college, you do the optimal policy from there on. And typically, optimal policy from college doesn't involve just drinking the whole day, right? So if you ever want to sue some high school counselor saying, I did get to the college, and I'm still not making any money. I'm having a good life, daytime, I'm sleeping, but I'm still not having any money. That's because you followed a different policy. It wasn't the optimal policy. Okay, so value of a state, optimal value of a state is with respect to the optimal policy. They're connected. Okay, so, and then we are trying to figure out what the optimal policy is, and then you do this in terms of value. So if you keep sort of iterating over the values and ever reach the optimal value, then from there you can get the optimal policy. In the same way we did for the finite horizon. Okay, and then the other interesting question is, as I said, this is going to be stationary. There is an optimal stationary policy, and there is also an optimal non-mixed policy. That means you don't have to use a mixed policy. That means you can have a stationary policy which says whenever you are in state S with 0.7 probability do A1, 0.3 probability do A2. That's a stationary policy, but that's mixed policy because it's actually using a passing. Okay. So the theory essentially, which we'll only touch briefly, essentially says there exists an optimal policy that is stationary if there is an optimal policy at all. Okay, and then the value function is the optimal value, the corresponding to the optimal policy is the optimal value function, V star x. Now the question is, how do I compute V star x? And the idea is, if you go back to this picture, okay, if you just sort of, kind of an intuitive idea is to keep increasing the number of iterations that you would, the horizon that you're going to live. Okay, infinite horizon MDP is sort of nothing but finite horizon MDP with t tending to infinity. With t capital T, the number of stages tending to infinity. Right? Okay. So in some sense, and then one of the other interesting things is that so in some sense, if you start here and I start with V0, and then I kind of get the V1, which is not like there is no stage per se, but essentially, the act as if there's one stage to go, and then you get the V1. Then V2, which is the 2 stages to go. V3, that is the 3 stages to go. And then keep going backward until V100, let's say. If this MDP does have a stationary optimal policy, then this V better start converging. Even though V0 and V1 and V2 are different from each other, if V100 is still just as different from V101, you're not going anywhere. Okay? So in essence, what we have is, the intuition is that, if you keep doing this backup, this is the Bellman backup that you used from V0 to come to V1, and then V1 to come to V2. If you keep doing the Bellman backup repeatedly on the value function, okay, then if you do have an optimal value function, you will converge to it. And then you just have to prove a separate theorem saying there will be an optimal value function and you will converge to it. Okay? So from an algorithm point of view, essentially, you're just doing the same exact algorithm. In this algorithm, V1 means 1 stage left to go, and then you remember that, and V2, 2 stages left to go, and you remember that. If you're using the same algorithm for the infinite horizon, all you really care is you write Vk in terms of Vk plus 1 in terms of Vk, and you keep doing this until the difference between Vk and Vk plus 1 is non-existent. Okay? If the value functions in 2 different iterations are the same, then you have converged. Okay? In particular, if they don't, because we're talking about real numbers, and you know from elementary programming that if you ever write a program which depends on 2 real numbers being actually equal, that is a great way of writing unending loops. Right? Okay. Instead, what you do, you essentially have to say the difference between them, the absolute value of the difference between them is somehow bounded by a very small number. Okay. So in particular, I have Vk. Yeah. So I have a Vk, which is the value function at the kth iteration of my algorithm, and then the Vk plus 1. Value function of the k plus 1 at the k plus 1 iteration. I take, since these are vectors, remember that the value functions are not single numbers, they are basically giving values for each of the states. So value functions are really vectors over states. So you need to talk about, the difference between 2 vectors, that is fine, but then you need to talk about the size of this difference. And for that you normally use vector norms, right? And for most of the MDP theory, we'll use max norm. Max norm is max norm of a vector is the absolute value of the maximum coefficient of the vector. Maximum coefficient of the vector. And if these 2 are exactly the same, the difference vector should be 0, so the max norm should be 0. If not, then you're talking about what particular dimension are they maximally different and how big is that. And if you somehow can keep it less than epsilon, then you can stop it. Did it make sense? Okay, so I'm essentially doing the finite horizon MDP where t is not given. In the case of finite horizon MDP, t is given upfront. Okay, here t is not given. I just basically, because there is no actual finite number of stages, and I just keep updating my value function until it converges.
This looks a lot like authorities and hubs.
What?
Authorities and hubs.
Yeah, I would say the opposite way,
Okay.
which is that is a special case of this. Okay, basically page rank, computation, all these things. Of course, this is just a fixed point algorithm ultimately. That's all you're looking at. Okay? And in fact, that analogy will help you in all sorts of improvements you can make to this algorithm. Okay. Okay. So. Okay, so actually this value iteration, we don't even need the value iteration. To do the value iteration, essentially all you have is this Bellman equation, okay, which is saying V star of a state must be equal to the reward of that state plus this is, if you are in that state and you do an action A and you get to S dash, then you take the V star of S dash, you take some expected value of the reward, and you take the max over all possible actions you can do. And since that is the reward you get, if you are here, that's the reward you get one step after this. So that has to be multiplied by beta. That's the big part. That is something that you did not have. That is the thing that you didn't have in the finite horizon case. Okay, and one other thing is that in the finite horizon case, you would have said Vk star is in terms of Vk minus 1 star. Right? And now there is no k and k minus 1 because, at some point of time they have to become the same. Okay? In particular, essentially, this operation you're doing it on a value function. You're doing Bellman backup or a value function to get a new value function. You keep doing this until the value function before and after remains the same. Okay, and so the optimal value function is a fixed point of the Bellman backup operation. Okay, and this is Bellman backup operation. Okay. From an algorithmic point of view, you just do this many, many times until you essentially find that the distance between the two iterations is less than some pre-specified threshold, then you're done. Okay, yes?
Just so that how do you make sure, assume that Vk minus Vk plus 1 is smaller?
Because you do have the values in front of you.
Yeah, but
if they start diverging, you mean?
Yeah.
Okay, that is the theory. Okay, and the reason it works, let me get back that in a minute. It turns out that Bellman operation has a property called the contraction property. And essentially, when you apply Bellman operation to two value functions, okay, then the distance between the Bellman applied value functions would be less than the distance between the original ones by at least a factor of beta. The beta is the discount. And this is enough for you to make sure that so every time you apply the Bellman operation, okay, so in fact now since I said that, let me get there. Okay, so every time you apply Bellman operation for the V and V dash, two value function V and V dash, the distance between VV and VV dash is less than distance between V and V dash by a factor beta. Okay? Now, if you think one of these V's is a V star, then BV star minus BV dash would still be beta times V star minus V dash. Right? Okay, because BV star is the same as V star. Okay? And so that's essentially the property that helps you ensure that you would reach the fixed point. And the reason this holds, since we are here, let me also point that out, that the reason this holds is reasonably easy enough for at least one of the simpler proofs. is just this. If you have two functions, here is f and here is g, okay? And if you ever take the difference between the max over max value of fa and the max value of ga, okay, in this max value of fa is here, max value of ga is here, okay? So this difference is going to be less than or equal to the difference between the max of f and g at the same point. Okay, so this is the point where f and g differ maximum, and that difference is indeed higher than that difference. Okay, you can use that property to actually prove the contraction property. Okay, so there are like two things I'm saying. One is contraction property holds, and because of the contraction property, the vectors will come closer and closer to each other, basically to V star, and so essentially you will converge to V star. Okay, and then the reason contraction property holds is that. Okay, let me, before I lose too many more people, let me show a picture. Okay, this is an MDP for, it's an applet. Actually, you can just say value iteration applet, you will get it. Okay, this runs with Java. And so it's sort of get a sort of an intuition. You can play with this. So in this particular case, I put, okay, I'll reset. I'm going to decide what my discount factor is. Okay, let's say I put discount factor to be 0.9, and I'm going to step. Okay, and when I step, in the first step, essentially, the value function is going to be set to 0th step. The value function is set to the rewards. It turns out in this, the reward for this state is -10, this is -5, and this is +10. You can see, white on green. Okay, that's +10. And given that, what should the optimal policy be? That's what we're trying to find. And to do that, we'll first find the optimal value, and once I know the value, I know the policy. Right? If I know the value, then for each action I can do from this state, I know the expected value that I'll get from the neighbors for that action. And I pick the action that has the maximum expected value. That's it. Right? And so what value iteration does is it essentially only updates the value, and until the value function doesn't change too much. And then it stops, and then it converts into a policy. Okay, what this applet actually does is it also shows you at any given iteration, it also shows you if you start there with that value function, what would have been the policy. Notice that for any given value, there is a policy. Right? So that's a good thing to play with to get your intuition straight. So I'm stepping here. So essentially, after like just one iteration, notice the minimum obvious thing is everybody around the good guy will say, let's go into it. Right? In particular, before, one of the interesting things that happened is, it's kind of today. Previously, the reward for being in this state was 0. So V0, the 0th iteration value set 0. And then after one iteration, you realize, yeah, I thought I was a loser, but I have friends in high places. So I must not be all that much of a loser. As long as I know how to reach them, and I have an action, and I have a choice. Right? And so that's what this guy realized. And I do have friends in high places. It's just that I don't have a totally foolproof mechanism for reaching them, because I have an action which sometimes will get me to my friend, sometimes will get me to somebody else. So if I do the action that has the highest probability of getting me to my friend, then that time I will get the expected value of 6.3. Okay? Now, having decided that, now of course I also know the policy in this particular case. I have a rich friend here, a loser here, a loser here. I would obviously do an action which goes this way. Right? And the same situation, same way, these guys essentially at least realize, let's avoid doing this action. Because I'm going to die. Everything else is fine. So all others are equally good. Okay? And so the four-sided means all actions are equally good. So any of them can be arbitrarily picked. Okay? And so I step further more, I get some more green. So green essentially means positive value. Red means negative value. No? And also, if you don't change, if you see the numbers, as the numbers are changing, that's how the value function is changing from iteration to iteration. Okay, you notice that actually it used to be 6 something and it's still 6 something here. So this hasn't changed much at all really. It's almost stabilized. Okay, the reason it did change, by the way, is because in the previous iteration, these two guys still thought they were losers. Since they said we are losers, you said, well, you must be loser. So I would have not as much of a value. But now they realize that they can be, in fact in this case, they also realize that since these guys are close to this guy, and they can be richer too, because by doing this action, they can improve their action. Okay, so that's essentially, you can keep stepping through this a little bit, and you see at some point of time, the changes sort of reduce. It still is changing a little. Okay, and if you kind of step multiple times at some point of time, you notice that it's almost kind of not changing too much. If you can see that matrix. Okay, now here's my question. Suppose I were to take, this is taking point, I put 0.9, it's sort of stabilized, the value function has sort of stabilized. Now one of the other interesting things is, the value function is still changing, right? Is the policy changing?
No.
Did you notice that? That's actually one of the reasons why we even learn about policy evaluation. Because many value functions may correspond to the same policy. And there is only one unique optimal value function. Okay, and so when you're looking for the optimal value function, you essentially are checking the distance between the previous and the next iteration vectors of the value function. And you are just too busy, until you drive down that residual. But unbeknownst to you, nobody is going to be impressed because everybody has decided and they're not changing. If a policy function hasn't changed from one iteration to another iteration, okay, that means the policy in this case has difference. Yes?
Can I ask a question regarding one of those, the really good spots, specifically look at the one on the top right, 6.01. It says that all 4 actions are equally good. But
which one?
If you top right, the 6.01.
Oh, here, yeah.
Yeah, all 4 actions are equally good, but if you look, the neighboring positions are not. So the bottom one is a 5.57, or the one to its left is a 4.97. So why does it not prefer that action?
It depends also on the, actual probabilities of the actions.
Yeah, because it's 6.46 downwards and 6.01 upwards. So
yeah, I mean the answer, this is what I'm not a program. This is a program. This does exactly what we want us to do. And make sure that if you have questions like that, figure out why it is doing it. It depends on, of course, one thing that I didn't tell you is in this applet, it is actually using some probabilities for each of the directions. I don't know whether it's using 0.8, 0.1, 0.1 the way we did before, for example. That might matter. But most of our intuitions can still be had from just what it's doing. Now, the point that I wanted to ask is, it's still sort of, value function has not converged yet. Suppose I were to change my beta. Suppose I want to change my beta. If I go from 0.9 to 0.5, do you think the value function will converge faster or slower?
faster.
How many people said slower? Why slower?
Because we think that means we
Think about extremes. Let's set beta equal to 0. Always do extreme analysis. When beta equal to 0, you're done, man. Right? Where you are, you are. RS all the time. So you converge after first iteration. Do you see what I'm saying? Whereas if I make it not 0.9 but 1.0, that's the other extreme. I carefully kept beta to be less than 1. Because if it is equal to 1, it does not converge. And one way of not converging at all is converging really, really, really slowly. Every time you see it's still changing. Okay, so that's something that you can figure out just from this, right? Essentially, now if I were to make it 0.5, okay, then reset everything. I made it 0.5 now, okay? Now if I step, again, it starts with the same reward function, okay? Now let's see how the done, right? Basically it's done. Okay, now of course if you put 0, it's done right away. Whereas if you put it 0.95, it takes even longer to converge. So the number of iterations that the value iteration takes is going to be a function of gamma.
But the policy that is this time is different from that was last time.
And are you surprised? Why should you be surprised? If you change your gamma, if you change your discount factor, then, if you had a 0.5 as your gamma, you should not be wasting your time in grad school. You would have dropped out from high school and made the maximum money you can make with that. Because you don't really believe that $10,000 a year from now is worth that much. So in fact, yes, the optimal policy will change. It is supposed to change. You see what I'm saying? Okay. And in fact, one of the interesting things, you can play with this. I think, I don't quite remember. I just before coming to the class, I remembered that there is this applet, so I put it up. I don't remember. It's been a while since I used it. I wonder whether I don't remember whether you can actually change, for example, the way to set the initial rewards. One cute thing you can do is put myopic rewards in the middle somewhere. So for example, put like instead of putting everything 0 and 1 minus 10 and 1 10, you put everything 0, 1 plus 10, and a couple of plus 3 sprinkled here and there. Right? And when your beta is close to 0.9, you will avoid the 3 and still get to 10. Eventually, you will aim for the 10. When your beta is close to 0 or be close to 0.5, you'll take what you get. That's exactly what high school students are doing. Right? They're getting whatever is the job they can get right then, rather than wait until PhD with the hopes that you will get much better job. Okay, and world is interesting exactly because there are all these distractions. Okay, so for example, the graduate student population was very high in the years there were no jobs in the industry. Okay, whether I believe graduate studentship is the best thing or the worst thing, I realize why people are in the grad school. They're waiting for jobs. I think jobs are a distraction. Okay, I think you should do PhD. And I think you will get to much bigger heaven after that. But you don't believe me. You look at, what you do is the same as what I do, what I would suggest you do, if in fact there are no jobs anyway. Whereas if I put a couple of jobs which are like distractions, you will actually not do the optimal thing if you have low discount factor. Do you see what I'm saying? It's like, so you're going to your exam and somebody offers you an ice cream, you say, okay, I'll just hang around here and take an ice cream now. That's classic case of your discount factor is extremely low. Right? Okay, so you can play with this to get more interesting ideas about whether your intuitions about value iteration are mixing with the actually what the algorithm does.
I have a question.
Yes.
Is Bellman contraction function used in finite horizon also?
Yeah. Bellman is the backup you use everywhere. But notice that in the finite horizon there is no beta.
Yes, that is what I was concerned.
And so, if there is no beta, then the contraction is no contraction. In the sense there is no bound that you're not guaranteed to get any closer unless you have a beta, which is less than 1. Right? If you set beta equal to 1, then essentially it says dv dash minus dv star minus dv is less than or equal to v star minus v. What good does that do for me? It doesn't necessarily guarantee convergence right then and there. Okay. So now, given, so how do I act? If at any given time I have a value function, and if the value function converged, then I know how to just convert it into the policy. If it hasn't yet converged, and if you feel like not playing this game anymore, just take whatever value function you have, convert it into the policy, use that policy. Okay, so in fact, one interesting idea is, if you only do k iterations of the value function, that's like doing k step look ahead. Okay, in fact, if you remember in my picture, for the 0.9 case, which was the more interesting case, in the 0.9 case, when I'm stepping through it, notice that this is the only thing with 10, and all of these guys were 0. After one